So in the previous videos I had solved the continuous beam using the flexibility method. So here we are going to solve a problem which is a non-sway frame, and we are going to analyze this frame using the flexibility matrix method. So before we solve the flexibility matrix, what we need to understand here is I have used the conjugate beam method to solve for slopes or rotations in the previous three examples that I solved for continuous beam. From here onwards, I am going to use a method called diagram multiplier method, which will be very simple for us to apply for such kind of frames. Okay, and one more thing, you can use the same diagram multiplier method for the continuous beam also. Okay, there is no restrictions that you should not use it. So what I'll do is to give you a perspective or to help you solve using the diagram multiplier method, I'll solve another continuous beam problem using the diagram multiplier method. Okay, so let us not get confused with this. What I'll do is I'll give an explanation of what is diagram multiplier, and then you can try to understand what is the difference that is going to take place between the previous method that we have solved and this method. Okay, so first of all, let us try to understand this given frame. In this given frame, let us first identify what are the number of reactions we have. So looking into this frame, we can identify there are 3 reactions at joint A and there are 2 reactions at joint C. At joint A, we know that there is a vertical, horizontal, and there is a moment reaction. Then at joint C, we have only 2 reactions. One is horizontal reaction, the other one will be of vertical reaction. So the total number of reactions will be 5, and we know that in this frame there are 3 equilibrium equations which can be used. So 5 minus 3, it will be 2 redundants. Okay, so which we have to remove. Okay, now in this frame, what I'll do is I'll remove this joint. So if I remove this joint, I'm going to release these 2 reactions. After releasing this reaction, this is what the frame I'll get. Okay, so in the previous problems also we used to do the same thing. So in flexibility method, what we do is first identify what is our static indeterminacy. After determining the static indeterminacy, the number of static indeterminacies, equivalent number of reaction have to be eliminated, or they must be converted into redundants, or they must be released. Okay, so according to this given problem, 2 is our static indeterminacy. So it means what, I have to remove 2 of the reactions. So I am going to select this joint C, which is the pin support. If I remove this, I am going to remove 2 of the reactions. So this frame will be of released frame if I am going to remove this support C. Okay, after removing the support C, what I need to do is to apply 2 forces with respect to the 2 reactions that I had. One reaction was horizontal reaction, so I will consider 2 direction. So if this is the direction of X, it will be positive, and if this is the direction of Y, it will be positive. So that's why what I am doing is I am applying the coordinate system here. So I have applied the first coordinate as the horizontal force which is acting in the positive X direction. Then there is a second coordinate which is acting in the positive Y direction. So these are the 2 coordinates I have applied. So this is quite similar to that what I had done in the previous problems also. There I used to remove the moments, and I used to apply the unit moments, and before that I used to give you coordinate system, right. Similarly here also we are removing the 2 of the reactions, and wherever the reactions are removed, I am mentioning them with the coordinates. Okay, so there is one force which is in horizontal direction, which is my first coordinate. Then there is another force which is acting in vertical direction, and it is my second coordinate. So this frame, what I'll do is, again we'll apply the unit force. Earlier we used to apply unit moment. Here we are going to apply unit force. Okay, because the reactions we have eliminated are vertical and horizontal reactions. Okay, so that's why we have to apply unit moment. So you can assume it to be 1 kilonewton or something like that. Okay, so this frame, with respect to the coordinate system, I have to apply unit force, and after applying the unit force, I have to figure out what is my bending moment diagram. Okay, so for example, I'll take, so this is the frame I have taken, and first coordinate system is in the X direction. So I am applying the unit force in this direction, and I am determining how much is my bending moment diagram. Okay, now similarly what I will do is I will take the same frame and apply the unit reaction, unit force in the direction of second coordinate, and I will determine what is the bending moment diagram. Okay, so these 2 diagrams which I have determined are going to give me what is the flexibility matrix. Okay, so let us try to understand what I have done in this two frames. Okay, so as you guys have already studied the unit load method, so if you remember what is unit load method, you will be able to understand what this method will also deal about. Okay, so I'll just give a basic example of what is unit load method. In unit load method, what you used to do is, for example, if there is some load that is applied, 40 kilonewton something, if you want to determine how much is the slope and how much is your deflection, what you used to do is you have to apply the unit load at that particular point, okay, where you are trying to determine the rotation and deflection. Then we used to take the integration of these two moments, okay, the moment that is created from the load and the moment which is created from the unit load, and if you take the integration of that, you used to get how much is the rotation and deflection. So the extended version of this method is what my diagram multiplier method. So in diagram multiplier method, what we are going to do is that we are going to take the bending moment diagram of the load and we are going to apply another unit load, and we will take another bending moment diagram which is coming from the unit load which has been applied. So if these two diagrams are multiplied with each other, you will get to know how much is your rotation or deflection. Okay, so this is the method which is being used. So the chart that you see on the screen is going to help you determine the slopes and deflections. Okay, so let us do one thing. What we will do is, this is the release frame I have, and the load, the external load which is being applied to this frame is 40 kilonewton meter. So according to this 40 kilonewton meter, I would like to determine how much is the horizontal and vertical deflections that are going to take place. Okay, so the horizontal and vertical translations can be calculated by using the diagram multiplier method. So let us try to understand how that can be solved. So first thing what I will do is, I will take this frame and I will apply the external load which is been here. Okay, so for example, if this is the 40 kilonewton load which is applied on this frame, okay, now this frame is a release frame, there is no support like this here. So let us try to solve what will be the bending moment diagram because of application of 40 kilonewton load on this released frame. So imagine if I am applying a 40 kilonewton load at this point, the moment at this end will be 40 kilonewton. Okay, so on the other side also it will become 40 kilonewton. Or here also it will be 40 kilonewton, and the reaction over here will be also equal to 40 kilonewton. Okay, so the bending moment diagram would be somewhat like this. Okay, if you see this is the span which is BC. The span BC is having a rectangular bending moment diagram which is of ordinate 40 by EI. Similarly, for member AB which is of length 5 meter, the moment will be of 40 by EI, and the bending moment diagram will be of rectangular in shape itself. Okay, so if after solving this bending moment diagram, this is the bending moment diagram which is solved for this frame when a moment of 40 kilonewton per meter is applied at joint C. Okay, so this bending moment diagram I will call it as capital M. Okay, the bending moment diagram which is calculated on the frame by application of external load. Okay, so this is called capital M. Now similarly, what I will do is, I want to determine how much is the horizontal translation that is going to take place in this frame. So to do that, what I will do is, I will apply the unit load in the horizontal direction, okay, which is 1. Okay, so let us try to solve what will be the bending moment diagram because of that. So at this point, the load which is acting at this point, bending moment will be equal to 0. So if I calculate how much is the bending moment at A point, it will be 1 into this length. What is the length of this column? It will be 5 meters. So 1 into 5, the bending moment here is 5 and the bending moment here is 0. So it will be a triangular bending moment here. Now let us define whether it is clockwise or anti-clockwise. Okay, so you can see that here I have written it as here I have written it as positive bending moment diagram. Now here I have written it as negative bending moment diagram. So let us see why it is positive and negative. Okay, so you know this condition which is sagging and hogging condition, right? So if it is of hogging in nature, it is negative. If it is sagging in nature, it is positive. So you can try to understand here in this frame. Okay, when it is subjected to 40 kilonewton load, the load is applied like this. So load was applied like this. So because of that, this member will be created as a sagging condition. Okay, so this will be of sagging in nature. Similarly, the sagging will continue for the column also. So that's why these two bending moment diagram were positive in nature. Okay, now let us go to this beam. So this column, so in this column, how I am applying the force, this is the force which has been applied, this is the distance. So the moment that is created is in anti-clockwise direction. So that's why this bending moment diagram will be of negative in nature. So every time whenever you apply force, you must be able to understand whether it will create sagging or hogging bending moment diagram. If it creates sagging bending moment diagram, it will be positive. If it is creating hogging bending moment diagram, it will be negative in nature. And you should also remember the sign symbol here. So to create positive, if you are going from right to left, this is the moment. And if you are going from right to left, in this case, if it is in the direction of clockwise, it will be of negative in nature. You try to understand these two. Okay, so once you draw the bending moment diagram for the external load, and again you have applied a unit load in the direction of horizontal, now we can determine how much is the horizontal translation that can take place. So this can be calculated by multiplying the bending moment diagram of the loaded figure and then the unit load. Okay, so this is the diagram which is to be multiplied with this diagram. So you can see here I have written it as D1. D1 is representing the displacement which is going to take place in the horizontal direction. So displacement in the horizontal direction is equals to capital M multiplied by small m, M1. Okay, so capital M is the bending moment diagram which is created because of the external loading, and M1 is the bending moment diagram which is created because of application of unit load in the horizontal direction. Okay, so we are determining how much is translation at this point. So it will be equal to this diagram multiplied by this diagram. Okay, now let us do first thing. This is my member BC. The M by A diagram here is nothing. There is no M by A diagram here, but we have M by A diagram here. So it means what, this is something equal to 0. So 0 multiplied by some value will be equal to 0 itself. So these two will get cancelled out. Now what is the member left out? This is the member which is AB. So this is the member AB which is subjected to triangular load for unit load in the horizontal direction. Then because of the external force, this is the M by A diagram. So the M by A diagram of the external load multiplied by this should be done. Now you can go back and look into the chart. In that chart you can identify that there are columns and then there are rows also. Okay, now you can see that if a rectangle is multiplied by triangle, you can see an equation. What is the equation that is given to you? 1 by 2 multiplied by k into I into L. Okay, so like if I am multiplying this rectangle with the triangle, the equation will be like this: 1 by 2 into k into I into L. L is representing the length of the member, k is representing the value of ordinate in the capital M diagram, and I is representing the small I value. Okay, the ordinate of the M1 diagram. Okay, so you can see that here I have solved this condition. So D1 is equals to capital M multiplied by small M1. So 1 by 2 EI into 40. As I have taken the EI separately commonly, so it will become 1 by 2 EI into 40 multiplied by minus 5 multiplied by the length is 5. So D1 displacement in the horizontal direction will be minus 500 by EI. Okay, now similarly we can solve for D2. D2 is the displacement in the vertical direction. So what I will do here is I will apply the unit load in the vertical direction. So let me apply the unit load in the vertical direction and determine how much is my bending moment diagram. So I will take this frame and I will apply the unit load. So let us start from here. Here the bending moment is equals to 0. Okay, so what is the distance from here to here? It is 3 meter. So 1 into 3 is equals to 3. So that's why the bending moment here is 3, and the bending moment on the other side will be equal to 3 itself. Okay, and this 3 will get continued till it reaches till this point. Okay, so now here is your rectangular bending moment, and this this is a triangular bending moment diagram. This will be a rectangular bending moment diagram. So this is the bending moment diagram that is generated because of application of unit load in the vertical direction. Now let us determine how much is the displacement that is going to take place in the vertical direction. Okay, as we have drawn the M by A diagram for unit load being applied in the vertical direction, so this diagram has to be multiplied with the capital M. So see here, D2 is equals to capital M multiplied by M2. What is M2? M2 is the bending moment diagram that is generated because of application of unit load in the vertical direction. Okay, now we are determining how much is the displacement in the vertical direction, which is my second coordinate. So D2 is equals to M into M2. So what we'll do here is we have to multiply this diagram with this diagram, and we have to multiply this diagram with this diagram. Okay, so then it completes the multiplication of capital M multiplied by M2. Okay, as we know, this is triangle and this is a rectangle. If a triangle is multiplied by rectangle, you can see the diagram multiplier chart. In that chart you can identify it is equals to 1 by 2 into K into I into L. So that's why 1 by 2 EI into 40 into 3 multiplied by the length, which is 3. So this and this is multiplied, plus of this should be multiplied by this one. Okay, so as we know, if rectangle is multiplied by rectangle, you can see in the chart it is equals to K into I into L. So 40 by EI into 3 by EI multiplied by the length is 3 meter. So this completes the solution of D2. So if I solve this, I'll get to know how much is the displacement in the direction of vertical. Okay, so we have determined how much is D1 and D2. So D1 is minus 500 by EI, D2 is 780 by EI. So the displacement matrix will be equal to this one. Okay, now from this you have identified how to solve the displacement matrix, and you also understood what is the benefit of using the diagram multiplier method. So whenever or wherever you want to find out the translation or rotation, what you do is that you multiply the diagrams of the external load and you multiply the diagrams of the unit load applied at the point where you want to determine the translations. Okay, I hope there is no doubt. I'll quickly try to recap what I have done. So what I do is that to calculate the displacement D1 and D2, first I'll determine what is the bending moment diagram because of application of external force. Then what I'll do, I'll determine what is the bending moment diagram if the unit load is applied in the horizontal direction and vertical direction. So this is the unit load which is applied in horizontal direction. This is the bending moment that is created because of that, and this is another diagram which is drawn by application of unit load in the vertical direction. So after solving these two diagrams, I can solve for displacement. So displacement D1 will be equals to capital M multiplied by M1, and D2 is equals to capital M multiplied by M2. So these are the two displacements I have got. From these displacements I define the displacement matrix. So after determining the displacement matrix, the next step would be to solve for your flexibility matrix. Now let us solve the flexibility matrix. To solve the flexibility matrix, what we need to understand is what is flexibility. Okay, so we have already discussed about what is flexibility. I would like to explain it again over here. Now imagine if this is the frame, which is the released frame. If I am going to apply a unit force in this direction, and I would like to determine how much is the translation that is going to take place in the horizontal and vertical direction. Now see, if I am going to apply a horizontal force in this direction, this frame is going to translate both in horizontal and vertical direction. Okay, now similarly, if this frame is again subjected to a vertical force in the vertical direction, okay, so this is going to again translate. Okay, so I would like to see what are those translation by application of unit force in both the direction. So whatever the translation that is going to take place is our flexibility matrix. So in the simple method, what I'll do is I'll take this frame and I'll apply the unit force like this. So it might bend like this. So there is both horizontal and vertical translation that is going to take place. So the translation both in vertical and horizontal direction is our flexibility. Now similarly, the same frame can be applied with the unit force in the vertical direction. Okay, again this member can translate, okay, because of application of vertical force in the upward direction, this will again translate. So whatever the translation that has taken place both in vertical and horizontal direction will be our flexibility values. So what I'll do is I'll try to determine how much is the value of F11, F12, F21 and F22. Okay, so we know the flexibility elements, so let us start determining the flexibility elements. So I am going to determine what is the translation in the horizontal direction first. Okay, so let us understand like this. So if I am applying the horizontal force here, how much I have to apply to calculate the flexibility? I have to apply unit load. Okay, so if I draw the bending moment diagram for this, it will be like this. Okay, so this is your phi divided by EI. So this is the bending moment diagram which is generated because of application of unit load in the horizontal direction. Okay, now if I want to determine the translation, what I have to do? Again I have to draw a bending moment diagram of this frame by applying the unit load. So which means basically to calculate the flexibility of this element in the horizontal direction, I have to multiply this diagram with itself. Okay, so that's why I have written here, you can see in this equation, to calculate F11. F11 is the translation which is going to take place in horizontal direction because of application of unit load in the horizontal direction itself. So if this frame is going to be applied by a unit force in the horizontal direction, how much translation it has taken place in the horizontal direction, that is what I want to define. So that's why F11 is equals to M1 multiplied by M1. So if triangle is multiplied by itself, if triangle is multiplied by triangle itself, so what is the equation you have? 1 by 3 into K into I into L. So where K and I both are same in this condition, right? So M1 multiplied by M1 will be equal to 1 by 3 EI into minus 5 into minus 5 multiplied by the length is 5 meter. So you will get to know how much is F11. Okay, so what is F22? F22 we will go to M2 diagram. So in M2 diagram, what is happening here? So here we are going to apply a unit force in the vertical direction and we are going to determine how much is the translation that is going to take place in the vertical direction itself. So here what we will do is we will multiply M2 with itself so that I will get to know how much is F22. Okay, so here this triangle is multiplied by itself. Okay, then this rectangle is multiplied by itself, and you know what is the equation to solve them? They are given in the diagram multiplier. From that you can calculate how much is F22. So after solving F11 and F22, you can go for F12 or F21, which will be same itself. Okay, so what we are going to do is we are going to multiply the diagram M1 with M2. So as we know, this triangle cannot be multiplied here because here there is no diagram, so this will get cancelled out. So we need to multiply this triangle with this rectangle. So my 1 by 2 EI into minus 5 into 3 into 5 will give you how much is F11 or F21. So from this we can generate a flexibility matrix. So this is what the flexibility matrix that I have generated. So after solving both the flexibility matrix and displacement matrix, the next step would be to solve your force matrix. So as we know, the force matrix is equals to inverse of flexibility multiplied by negative of displacement matrix. So this is what the values that I have got. So as we know, in the first coordinate it is the horizontal force, and henceforth the value that we got was a horizontal reaction at C, and similarly the vertical reaction at C. So these are the two reactions which you are determined by solving the flexibility matrix. Okay, now after determining the force matrix, the next step would be to solve the other forces in the given frame. So we have determined these two. Now as we know, in this solution both the values are negative in nature, which means that the directions which we have considered are wrong. So we need to change the sign symbol of the forces. Okay, so let us take this frame, and in this frame as we know, this is the direction of coordinate that we had applied. So henceforth the force is, the horizontal reaction is going to be opposite of that. Now similarly here it was in the positive direction, again we have to change it to the negative direction. Okay, so these are the reactions that we got at joint C. Now let us determine how much is the moment at B and how much is the moment at A. Okay, so if you want to determine how much is the moment at B, what I'll do is I'll take the moment of these forces at the joint B. Okay, so MBC is equals to, let us go for this reaction which is the vertical reaction, 16.296 16.296 multiplied by the distance till B is 3 meter. So this is 16.296 into 3. This becomes the moment. But let us see whether we have to consider it as positive or negative value. So as we know, we are going from right to left. In this case, it is of clockwise in nature. If it is clockwise in nature, we have to consider it as negative, as we know the conditions, sign conventions. So if you know the sign conventions, according to that, if you are going clockwise direction, it will be of negative. If you are going anti-clockwise direction, it will be positive in nature. So minus 16.296 multiplied by 3 is negative value, plus of 40 kilonewton, which is positive, and I cannot consider this force because at B the distance covered by this force will be equal to 0, right? So anyhow this will get cancelled. So after solving this is what the moment I got for MBC. So for MBC and MBA, both will be equal, but they are opposite in direction, as we know this already. So FBC is equals to minus 8.88 and MBA will be equals to 8.88. Now let us solve for MAB. So to solve for MAB, what I need to do is to take the moment of these two forces. So let us take this force along A. So 69.296 multiplied by 3, I have to apply negative symbol as it is clockwise in nature. Okay. Next, plus of 40 kilonewton, again it is anti-clockwise, so that's why it is plus 40. Next, let us take this force, which is your horizontal force. So the distance covered by this horizontal force, if I take the moment at A, will be equal to 5 meter. So whether it is anti-clockwise, so if it is anti-clockwise, I have to take positive. So 2.667 multiplied by 5 is the moment because of this force. So sum of this will give you how much is MAB. So MAB is 4.447. okay, like this is how we can determine the reactions and also the moments for this given frame, and this is the analysis of the frame. From this from these values of movements and reactions, you can solve for shear force diagram and also bending moment diagram. So one more thing, as you can see here, I have written how much is the vertical and horizontal reaction. So VA, which is the vertical reaction, and horizontal reaction HA at joint A. So we can determine how much is your vertical reaction, horizontal reaction at A using these equations, equilibrium equation, which is sigma V equal to 0, sigma H equal to 0. So there are only two reactions, so VA and VC, HA and HC, and there is no external force being applied. There is no external horizontal or vertical force. So that's why we know this equation VA plus VC should be equal to 0, and similarly HA plus HC equal to 0. So if we solve this, you will get to know what will be the direction and magnitude of HA and VA. So this is how I have analyzed this frame. So what you can do is that from this frame you can draw for shear force diagram and bending moment diagram. Okay, so if you have any doubt while solving this problem, you can ask me the doubt. So we are going to solve more problems on the flexibility matrix itself in the coming videos. Thank you.